Hi everyone, hope you're doing well. So, in this video, I'm going to talk about how you can actually do a proper scientific analysis on the effect of Amazon's pullout from Google Ads. You must have seen, or you must have already been aware that Amazon has stopped using Google Ads as one of its channels for advertising, and that has happened sometime around late July. This has become really popular. There are so many articles and posts on LinkedIn and on X. So there's been a lot of speculation as to why Amazon has been doing it. I think the verdict is still out on that. But the point is that I haven't seen a lot of impact analysis. And by that, I mean not just a naive observation like, okay, what happened after Amazon actually stopped appearing in the auction insights. Has there been a rise since, say, July 22nd? So the date actually varies a little bit depending on the specific market, whether it's Amazon NL or Amazon.ca or Amazon.us or UK. So different countries, in different countries, Amazon has pulled out at different dates, but more or less within a band of, say, 3 to 4 or 5 days at a maximum. And what we've seen is that the plethora of posts are there around the speculation as to why Amazon has done it, but not so much a rigorous scientific analysis of the impact. So that's what this video is going to focus on, instead of just doing a naive observation. And by that I mean, like I said, a before after analysis, really. So, okay, so what happened to average CPC? What happened to impression share, say, starting from July 21st onwards to present day, and compared to the period before that? Now, the better alternative is to do something called a DiD. So DiD stands for difference in difference. It's literally like the difference between two differences. And just going to show you in a moment the regression equation, and from that you will be able to understand. But before that, also, like, the data set that we're going to work on, this is a dummy data set. From my own experience, to be honest, like, I've not seen too much improvement in CPC in the accounts that I have access to, and some of these accounts are fairly high spending accounts as well. But there has not been too much of an impact. But I think the fact remains that you should definitely do your own tests. Don't rely on the summaries or the aggregate reports from others. So definitely do your own causal tests, and this is what this video hopefully will help you do that. So this data set consists of four geos. So it looks at two sets of geos. One, the treated, which consists of two geos, and another set of controls, which is also consisting of two geos. So Netherlands and UK in the treated, Germany and Canada in the control. This is just arbitrary. This can have like different kinds of geos within it. And by geos here is basically, you need to have some sort of segmentation or dimension. So in my case, I've done this. So for instance, this can be two campaigns, from, this can be, suppose, the set of all campaigns from these geos. Basically, in this data set, essentially, you have, as you can see, multiple campaigns as well. So you have 10 samples per geo in both pre and post test period. So this is what the difference is really going to be like. What is the difference in treatment? What has been the difference on the treated variable, which is average CPC in this case, between the control and geos across the two periods? So that's the difference in difference. And this is what the data set is really going to look like. This is not going to be something that you will get immediately after you export data from Google Ads, by the way. So you will have to have the campaign. So for geo, this is just for simplicity I've done. Again, this can be like, suppose this is a specific campaign 1 for NL, campaign 2 for NL, like that. And these are all in the treated period. I'm sorry, these have all been treated. And you can see, belong to the treated group. Similarly, you will have campaigns which are in UK, which have also been treated, as you can see. And these are in the pre period, and you will also have the same sets of campaigns again in the post period. So that's how you're going to have to organize this data set. This will actually have like 80 rows, because as you can see, there are four geos, and then there are 10 in each, 10 samples in each period. So 80 rows essentially. And you will have this six columns here. So you'll have the geography, which is basically the campaign. You should have a campaign. This is just for simplicity's sake, not to have complicated campaign names here, for the purpose of this video, that I've kept it this way. Then you will have treated or not. So this is a binary column again. So either it will be ones or zeros, whether or not that belongs to the treated. So this means that Amazon may not have been present in all markets at all, right? or Amazon may not have pulled out of all markets. So depending on that definition, you could actually have this column here. And this is like period, which means whether or not this particular date belongs to the pre or the post period. This will be easily done again by you. This can be assigned depending on whether or not depending on the specific date for that that you've decided as your intervention, uh, as the period when, as the date specifically when Amazon did the pullout. And then you have CPCs, which obviously is something that you collect from Google Ads as well, apart from the geo data. And then you have whether or not it's in the post period. So this is so sorry, this is actually whether this is post in whether it is basically in the post period. Yeah. So this is how you create this data set. Now I'll quickly come to the regression equation that's going on in the backend. So this is the difference in difference regression equation, and you are basically using the target variable here, or the treated variable, as your CPCs. This can be impression share as well. So usually CPC or impression share, these are the two variables that we expect to be impacted most by Amazon. There can be like ripple effects on other variables as well, but to be honest, it's going to start from these two, right? Because the other variables can have other confounding factors as well. So these are the ones which will have direct impact. I've tried to also think of other causal impact analysis, by the way. Again, just to sort of take a couple of steps back, DID is one of those methods which are deeply rooted in the statistical tradition of causal inference, which dates back a long time. I can't go into the details in this specific video. I'm going to make more content around there. It's already out there if you want to explore as well. But you could potentially also have regression equations, and even in this case, other confounders. But to be honest, like, what are the other factors really having an impact here? I was not able to think of too many. I thought that this is the best way to do it. So the way this is the most skeletal structure actually for DID. Like, you have this column here, the treated, whether or not it's treated. This column here, whether or not it's in the post period, which is this one. And finally, the column for the interaction term. So the coefficient for this interaction term between these two columns, whether or not it's treated, whether or not it's in the post period, that's basically this beta 3 here. That coefficient will give you the treated effect, and that's what you want to estimate or extract from this, isolate from this model. And then you have an error term as well called epsilon. So I'll come to the next two a little bit later, but this is the regression, the core regression model. Again, you could potentially add more confounders here. This is what you are really obviously trying to predict, the impact, the treated variable, which is your CPC in our case. So hope that was clear. Now I'm just going to quickly move over to the code here. So the first of all, there is a data set generation here, because like I said, this is working on a dummy data set. And the way this has been done is we have introduced some sort of, synthetically, some sort of dip in the CPC in the treated regions. So those are the cases where Amazon was already present, but it pulled out. And the control, like I said, could be that Amazon was present and it still continues to be present, or was never present at all. In each of these cases, you can actually define them as controls. And then there is a visualizations of CPC over time, and then there's some bar charts, and we're going to come to a couple of more tests which are going to be robustness checks. I'm going to come to them in a moment. Let's actually first look at the output first, not go through too much code. So these are the direct regression results, from the OLS, and you can see that we have the dependent variable as CPC, like I said. So OLS is nothing but ordinary least squares. This is the simplest form of regression model, and you see this model is like very good in terms of its prediction of variance, expression of variance. Like, it's over 90% in terms of its R squared. Adjusted R square is also very good, obviously. And you also have the AIC, BIC, a lot of other values here. I'm not going to go into all of these, but like I said, the number of observations is 80 here, as you can see. So we have a degrees of freedom being 3. Now, these are important numbers. These are the different coefficients, as you can see. So the intercept is almost 0.8, and you have this interaction term here. This is in the negative, as you can see. And so the overall impact has been a dip, as you can understand. So essentially, That's what it means. Like if it is in the treated period and if it is in the post period, there's overall been a dip in the average CPC. So that's what it says, and you have a very significant p value as well. As you can see, for this interaction term, which is beta 3, it is much lesser than 0.05, which is the 95% level of confidence interval, the statistical significance corresponding to that. This is also the range, the confidence interval, and that is how it varies between minus 0.16 to minus 0.126. This is the variation of the coefficient. So this is the main model, and that's pretty much it. This is how you basically check whether or not there is actually an impact on the variable of choice. In this case, that is CPC. You could have done this for impression share as well. um, but the thing is that it is, like I said at the start, this is the most scientific and robust method. It is so because there are some robustness checks, there are some assumptions that go into the model, and you have to ensure that those assumptions actually make sense. So I'm going to talk about the most important one of these first, and then just quickly gloss over the remaining two. So this is called the parallel trends assumption. So this means that in the pre-treatment period, these two sets of geos, or these two sets of values that you've taken, across control and treated, uh, the one which is going to be treated, so you can see that 0 stands for not treated, and 1 stands for treated. So these are those two graphs. They should have more or less a parallel trend. They may not be necessarily same in value, like they could have significant difference in actual magnitude in absolute terms, but they should more or less follow a similar trajectory. And you can see that there is some sort of similarity. It's not exactly real, and this is reality. I mean, this is how I also built into the data synthetically, this sort of um, some sort of messiness. It's not precisely parallel as well, which is to make it more realistic. You see that this red hashed line, this dotted line, that this vertical line actually represents your intervention. That's when Amazon pulled out. So that's going to be around, say, 22nd of July. So you can see that this orange line dips sharply. This is the treated, so that's where Amazon has pulled out. For the other regions it hasn't pulled out, so CPC has dropped sharply. So the parallel trend, for the treated geos, or the set of campaigns, in this case, by geography. So you can see that so the point here is that the parallel trend assumption, visually, from a visual inspection point of view, seems to have been this assumption seems to have been satisfied. But if I now come into the treatment effect part, this is a bar chart that actually shows the treatment effect. So during the for the control regions, the average CPC is actually very similar in the post and pre periods. But in the post and pre periods, for the treated regions, there's a significant difference in CPC, and this is basically the calculation that actually shows that the parallel trend effect is in fact working, because or rather that's been satisfied. Because if there was an impact, suppose, of this intervention even in the control regions, then it wouldn't make sense, because then your segregation doesn't work, and therefore the comparison doesn't work either. And then there is another thing which is called the placebo test, which means that there's a fake intervention that has been carried out for a false date. So remember, it was around July 22nd that we had taken the date for Amazon's pullout. And this time you see that instead of having this red hash line, we have this violet, I think, yeah, whatever that color is. So that dashed, or sort of hashed, or sort of dotted line is present around here. The reason why we do that is to sort of see if there is a significant change around that date or not, because you would expect the change, if any, to be after the intervention date, the real one. But if there's a change even before that, that means that the parallel trend presumption is not there, or it's actually violating some other important assumptions as well. Okay, which is that the effect is only due to the intervention in question and not due to something else. So that is also a test that you need to carry out, and you need to do the regression again separately. But this time your data set changes, right? Because remember, the data set also has this column for, say, post period, and your post period basically changes because you now have a date which has been shifted earlier. Hope that makes sense. And you do that uh, test, and you see whether or not there's whether or not there's a significant difference between these two values. And you'll see that whether or not there's actually a significant difference. So that is the assumption here. And you see that there's actually some difference, which is not a lot, but that's a problem also. Like that doesn't explain a lot, but that's also a little bit of a problem, because ideally you would want these to be very similar. There should not be too much of a difference here. Okay. But you see that in fact the CPC actually increased for the treated region. So that's also yeah, kind of strange, to be honest, in this case. But the point is that this is the test that you should run, and ideally what you would have here is not too much of a difference between the treated and the control in this period. And before and after this fake intervention, this is a placebo test. And this is the pre-trend regression. This is where we only take into account the pre-period, and just again do a similar sort of analysis and try to see if there's really a difference or not. And you see that this is where we are taking only the treated variable. So if I go back to the regression equations that I was talking about earlier, so this is that regression equation, this is the pre-trend check, and this is where we take as you can see a different time num variable, and we have the treated variable again. And this is where we are only taking into account the pre-treatment period. And that is where you also have to check the coefficients and the level of significance. This is what you would expect to be not as significant, and certainly the difference to be pretty low. And you can see that the difference is pretty low, right? So that kind of shows that your you know pretend check assumption. So meaning that you don't have too much of an influence of any other factors or the intervention before the date of intervention, right? So that is basically what you're checking here. Again, like I said, this is not perfect. This is the data that deliberately has some messiness introduced into it, but that was something that I did on purpose. This is by design. All right, so this is the core equation. Again, this is the equation that explains CPC, just as a recap. And this is the data here that I was talking about. So you have an intercept, you have the treated column, whether or not it's treated, you have the time column, which says whether or not it's pre or post, and then you have the interaction term here. So hope this was useful. This is the main explanation. This is the summary of the assumptions and the checks, the parallel trends. There's sattva, which also says whether or not there is no spillovers, which should not be the case because we have separate geographies. That's the safeguard or the guardrail against the violation of sattva. And then you have no anticipation, meaning that the placebo test also shows that whether or not if you just shift the intervention date ahead of time, and see that whether or not the intervention or sort of the expected change is already happening even before the intervention occurred. We saw that this was not fully satisfied in this example, and that's exactly what you have to do. But you have to check the extent of the difference also, right? So if you do a fake, if I look back into the fake intervention test, you have to check just how much was the coefficient. The coefficient wasn't very low, to be honest, at that point. But you see the level of significance also is important, and in this case it's kind of a little confusing because it's also significant, this interaction term between placebo post and treated. So that's a bit of a concern, to be honest, at that point. So that's something that you have to test, and you have to see whether or not the robustness is actually the robustness checks actually satisfy the conditions that are required in order for this to be a valuable model. So hope this was useful. That was my overall idea behind how you can actually scientifically do this analysis. I know there can be potential confounders, but to be honest, like, I did not find why the CPCs would suddenly change if everything else is remaining more or less constant. So I thought that this is probably the best equation that you can go ahead with. But Feel free to add confounders if you think that that could have, in your case, impacted the CPCs in the post intervention period as well. But yeah, let me know if you have any questions. This is a big field, and we can have different kinds of approaches to it, but it should be very strongly rooted in causal inference methodologies, because that's the more scientific and rigorous way of doing it. So yeah, thanks for watching. Do check out for my next videos, and I'm going to talk about this more and more, and explain the equation and the math a little bit more. But for now, that's all. If you have questions, do let me know in the comments, and I'll see you in the next one. Thanks for watching.